Hi, this is Cross and Nabla, and today we're going to be covering over section 11.7, motion in space. Now this is kind of an extension of our previous section, 11.6, covering lines and curves in space, and now we're generalizing it to motion of curves and lines in space, right? In order to do that, we have to kind of cover over some stuff real quick with position and velocity and acceleration, and also the extension of parameterizing curves into 3D. We kind of went over this in our last section, but we say that we have it r of t as a vector. We have an x of t, y of t, z of t. In calculus 2, when you may have done parametrics, it may have just been these two respective components, but now we're extending it to the third dimension. From our previous section, and also just from prior knowledge, we know that velocity is just the rate of change of your position function. So it'll just be equal to x prime of t, y prime of t, z prime of t, right? And then the speed is just your magnitude of your velocity, right? So you can write it as the magnitude of this, or magnitude of v of t, because speed is a scalar quantity, it's not a vector quantity, because it doesn't give you the direction, it just gives you a value, the magnitude of something, right? Or we can rewrite it as x squared plus vy squared plus vz squared. You can also rewrite it as like x prime of t squared plus y prime of t squared plus z prime of t squared, and so on. There's a lot of different ways to write it. And acceleration, we know, it's just the second derivative of position, or the first derivative of your velocity function. And then we can rewrite it like that. And you can also just do this when you're writing it in vector notation. And yeah, looking at this is kind of some of the similar stuff we've been looking at from section 11.6 with lines and curves in space, but now we're generalizing it to these three-dimensional curves. And what you're seeing on the left right here is this is the 3D projection of a curve in space and motion. You can see the velocity, position vectors, and acceleration vectors. And then on the right, actually, you're going to see the scale, the two-dimensional version. We're ignoring the z-axis, and we're going to see some interesting trends pop up with this later on. With straight line and circular motion, these are like the two most common ones you may have seen in physics already. So the first one, straight line motion, involves like kinematics. So that's like the first unit of like a physics 1 class you may have taken in college, right? And in order to do this, to solve for the velocity and acceleration functions, we have to take the derivative of the position function, right? So the derivative of the position function here would just be a, b, and c. And the derivative of that would be 0, 0, 0. And in this case, we don't have an acceleration for any of these, so we can also write it as our 0 vector. And this is just uniform constant velocity straight line motion. For circular motion, this is something that involves like centripetal forces, rotations. In our cross product video, we covered over torques, right? That is part of what circular motion is as well in physics. And in this example, they want us to sketch the trajectory of the object. So feel free to pause the video, try this on your own. Yeah, so let's try this. So apologies for my poor trying, but the idea of the sketch that's supposed to model a circle with a radius of 3, and we have it right here. Find the velocity and the speed of the object. So we have to take the derivative of our position function. So v of t, we know it's just r prime of t, so we just take the derivative of each of the components on the inside separately. Get the magnitude of that to solve for the speed. And then we're going to get 9 sine squared t plus cosine squared t. This just goes to 1, so it's going to be 3 as our speed. And it doesn't specify the units, so we're just going to leave it as 3. The acceleration, we just take the derivative of our velocity function. So let's get our velocity function real quick. Right, and then let me just erase that. And then what we can do is take the derivative of this and get this. Now, something that's interesting with this is that we get back the same thing as our position function. Only difference is that it's negative, it's not positive, right? So you can see right here, there's the negative, but up here, there is no negative on either one. That's an interesting thing that we're going to see with this. And for part D, we're going to sketch the position, velocity, and acceleration vectors for this. So let's just call blue our position, green our velocity, and orange our acceleration. So blue is our position. This is what it is at 0, pi over 2, pi, 3 pi over 2. And this is just the rotations around the circle, so we can draw some arrows to indicate that, how that's the movement of the particle around the circle. Its velocity is going to be different, and we can identify it here, so we can plug in 0, pi over 2, 3 pi over 2, and 2 pi and solve for that. We can do it real quick. So when t equals 0, what's the vector pointing in the x direction? It's going to be sine of 0, so nothing in the x, but it's going to be 3 in the y. So it's going to go up like this. And then for pi over 2, it's going to be negative 3x. It's going to be cosine of 0. It's going to go like that. And pi, it's going to go 0 in the x, but negative 3 in the y. So like that. And then 3 pi over 2, it's going to go negative 3 sine 3 pi over 2, which is going to be 3 to the right, and then 0 up, so like this. And then our acceleration is just going to be opposite of our acceleration is going to be opposite of our position. So our position is going across, our acceleration is just going to point straight in. And in physics, we cover this topic. It's called our centripetal force. So if you have an object right here and it is experiencing towards the center, that is because of centripetal acceleration, where you would have your MAC equal to mv squared over r, and then you would use Newton's second law to solve for it. Normally it would be like a gravitational, the force of gravity attached to it, right? And as you can see, there are some interesting trends that we're picking up on with this, is that the acceleration is negative of the position for circular motion, and the velocity is always tangential to the position. That's a couple of interesting trends we can see right there. And for given this, we can generalize this idea that we just talked about with position and velocity being tangent to each other, right? And in this case, we can say that it's actually orthogonal, and this is given by a proof that we can cover over real quick. So what we would have to do is take the dot product of these two vectors, because the position and velocity are two separate vectors that we can dot and see the angle between them for circular motion. Let's just say we have our r of t equals some r cosine t, r sine t. This is like a standard one, and this is going to be generalizable to all circular motion. In this case, It's going to be r negative sine t, r cosine t, and we do r dot with v equals this. It's going to be negative r squared cosine t sine t plus r squared cosine squared, not cosine squared, cosine t sine t, and they both have common factor of cosine t sine t. This just cancels, therefore it's 0. Given our definition of the dot product, it's also just going to be magnitude of r, magnitude of v cosine of theta. Doesn't matter what the magnitudes of these are. It's going to be cosine of 90, which means that these are going to be orthogonal to each other. And as we can see right here, that makes sense given what we have, right? If we also just plot it, we can see that it is going to be parallel to each other. They're going to be tangent to each other on the graph. Like, for example, these two are perpendicular to each other or orthogonal to each other. We plug in cosine of 0, we get 1, so we get 3 in the x. We get 3 here, 3 here, and 3 here. We get these to be perpendicular and these to be supplemental to each other. So those are a couple of trends. And we can actually show this with taking the acceleration function and actually dotting it with this. So we can get a of t equals negative r cosine t, negative r sine t, and we do r dotted with a equals to, and we can just do this one real quick. So it's going to get us negative r squared sine squared t minus r squared cosine squared t. It's going to get us negative r squared. And we know that the magnitude of both of these from our definition up here would be r squared cosine theta. So the r squareds actually cancel out, in fact. Now that we're left with negative 1 equals cosine theta. On our cosine sign, that would be cosine of pi. So cosine theta equals, so cosine inverse of negative 1 equals pi. And that's how you would derive that. And that's how we can show it up on here as well. It's pretty cool. Now, for example 2, feel free to pause the video and try this one on your own. This one involves knowing the formula of a sphere, so that's going to be x squared plus y squared plus z squared equals a squared, and working from there. So yeah, feel free to pause the video. Okay, so we want to make sure that this object moves on a sphere given this trajectory. So we know that's going to be x squared plus y squared plus z squared equals this. We're going to map it onto this. And then we can do 3 cosine t squared plus 5 sine t squared plus 4 cosine t squared. This becomes 9 cosine squared t plus 25 sine squared t plus 16 cosine squared t. This becomes 25 cosine squared t plus 25 sine squared t. So that just becomes 25 equals this whole quantity. Kind of bad drawing with y there, but then we can figure out our radius should equal 5. And it maps on perfectly. Find the velocity and speed of the object. So now that's just us taking the derivative of the position function. So we can write the position function down here. So it's going to be r of t equals the derivative of this, so it's going to be v of t. We can just write it like that. And at this point, these are pretty simple trigonometric derivatives, so I'm just going kind of quickly. And this is what our velocity vector would look like, and this is also going to be orthogonal to our position vector. And if we take the magnitude of this, we're also going to get, I'm going to skip over this one kind of quickly, but you hopefully get the idea of what we are doing. So this is going to become 25, because I'm going to add up the sine squared t's together. So this goes to 1 equals magnitude of v of t. So magnitude of v of t equals 5. Nice. And now we get to two-dimensional motion in a gravitational field. Now, I mentioned earlier in this video that this is going to be a lot of like physics applications, and this part right here is going to be the heavy grunts of it, right? So a lot of this is just going to be taking the antiderivative of your acceleration to get velocity, antiderivative of velocity to get position, and to rederive the kinematic expressions that you may have had to see in physics 1 or been forced to memorize, right? So now this actual derivation to understand why these equations work the way they do. So consider an object moving in a plane with a horizontal x-axis and a vertical y-axis subject to only the force of gravity. Given the initial velocity, v naught equals u naught, comma, v naught, and the initial position, r naught equals, r of 0 equals x naught, comma, y naught. The acceleration of the object for t is greater than 0 is described like this. And the velocity would be to take the integral of this, and you take the integral of this from, it's going to be, you're going to be getting from 0 to t. Actually, let's just leave it like this. It's going to be some constant c negative gt plus some constant c, right? But our velocity is also given an initial condition that 0, it's going to be u naught and v naught, so it's going to be u naught negative gt plus v naught. And you take the antiderivative of this again, and you would get u naught dt, comma, negative gt plus v naught dt. And then you would get u naught t negative 1/2 gt squared plus v naught t plus, oh, I forgot the x naught here, plus the y naught here. And for a lot of your kinetic equations, this is what it gets down to, right? And if you're familiar with physics, a lot of these formulas and upcoming examples are going to make a lot of sense given our previous work, right? Example 3. A ball's hit from 3 feet above home plate with initial velocity of v naught equals u naught v naught equals 80 feet per second. Neglect all other forces than gravity. Find the position of velocity of the ball between the time it is hit and the time it is first hits the ground. So applying these equations from above, try and solve for when the ball will hit the ground, right? So feel free to pause the video and try this on your own. Okay, let's get into it. So r of t is equal to 80 t, because 80 is our velocity in the x. We have no initial position of the y. No, we have no initial position in the x, excuse me. We do have it in the y. Our x naught is equal to 0, 3, because it's 3 feet above home plate. And if we want to like imagine this, right? We start at the origin, right? The person hits the ball here, and then it's going to go up, right? That's like the general idea. And this distance right here is 3 feet. And in fact, when we use g, we're often going to use negative 9.8 meters per second. But this problem is a little bit different because it's in feet per second, so we have to do the conversion from meters to feet. We get negative 32 feet per second. It's annoying, I know, because we're usually used to using the metric system, but in this case, we have to use the imperial system. And now we just have to plug and chug the rest of this into here. So it's going to be negative 16t squared plus 80t plus 3. And then we take the take the derivatives to get the velocity vector. So we're going to get 80, which checks out, and then we get negative 32 t plus 80, and then 3 is a constant, so that's all good. Show that the trajectory of the ball. Oh wait, sorry, no, we still have to finish part A. Excuse me, we forgot a part right here. And now we have to find the time from the ball's first hit to when it's first hit, and then until it hits the ground. So we have to take this, because this is the relevant part. We're looking when the ball's in the air and when it's going to fall to the ground, right? So we can use our good old friend, the quadratic formula, to help us out. And then we can just apply the formula. So just doing the math in my head at this point. And given what we got for t is approximately equal to 5.04 seconds. And then we are going to plug in this for our v and our r equation. So if we know that r of 5.04 is this, it's going to approximately give us 403 feet, and then 0 in this. Our velocity is constant in the x. It's going to be 80. It's going to be negative 32 times 5.04, which gets us going to get us negative 81.28 feet per second. And then part B wants to say that we want to show the trajectory of the ball of the segment as a parabola. What we can actually do, this is a neat trick that you may have learned in Calculus 2. It's a nice little parametric substitution, excuse me. You get this, and you have your other equation. Right? And then we see that this is y. We can see that y equals negative 16 x over 80 plus 80 x over 80. And if you were to model this on Desmos, it would give you a parabola. And for part C, we kind of already did this, so just stealing our answer from above, we got r of 5.04, which is just going to be 403, 0, so 403 in the x direction. The maximum height of the ball, this is like a standard Calc 1 question where we're given like the position function, and we're supposed to figure out when is, we're given the velocity function, we have to figure out when the position is at its max, right? So if we know that this is our position function, actually let's just take our velocity function, because I just realized we have that here. We can solve for when t is equal to, when the velocity in the y direction is equal to 0, because in standard projectile motion, we have an object going like this. there's no velocity in the y direction, right? So it's gonna just be 0 at that point. It's only gonna be x, right? So we can say that it's gonna be t equals, we're gonna say that 0 so we divided that by 8, 2.5 seconds. I plug 2.5 into our equation, our y equation from above. We can get that it's going to be this right here. So we can do negative 16 times 2.5 squared plus 80 times 2.5 plus 3. So this is going to be 200 plus 3. This is going to be 6.25. So it's going to be minus 100. It's going to be 103 feet off my very quick math estimates. And right here, does the ball clear a 20-foot fence that is 300 feet from home plate? So we have to refer back to our equation from above. At this point, I've had to write this down so many times. I memorized it. It's going to be 80t plus 80t plus 3. We solve for when it's 20 feet in the air. Wait, no, we're going to actually solve for when it's 380 feet across. So we're going to do 380 divided by 80 equals t. T is equal to 4.75. And we're solving for the in the x direction first because it's just easier than solving the whole quadratic, right? Because you might get multiple different answers for the quadratic. And then we can plug it into here, and then we can get our answer and just by doing plug and chug. And this part should be greater than 20, but we can double check. I have my trusted calculator by my side. Plus 80 times 475 plus 3. It clears it by just 2 feet, so that would be a home run. And example 4, we have a small projectile that is fired over horizontal ground in an easterly direction with an initial speed of 300 meters per second at an angle 30 degrees above the horizontal. So this is going to be a 3D model, in fact, and we can sketch this after we read the question. A crosswind blows from south to north, producing an acceleration of the projectile 0.36 meters per second squared to the north. Where does the projectile land? Okay. Before you want to pause the video and try this on your own, let's just get all the components that we know out of the way. So we know that R and T, right? Let's actually put R of T a little bit further away so it's easier for me to write out the rest of this. So we know that it's going to be like this, and this is X, Y, and Z, and if we just look at it from an XY perspective, like this, we're just projecting this as like a 2D thing, right? We're saying that Z is held constant. We're going to see that our acceleration north here is going to be this 0.36. So we know that. So we know that that's going to be in our Y direction. And then we have 300 meters at an angle of 30 degrees above the horizontal. So it's going east. So east is like this. So this is going to be 330. But then it's also going like this. Also, since it's meeting at the x-axis, it's going east. It's going up and east. So that means we know that it's going to be something like this. 300 cosine of 30. Nothing else. 0.18 t squared. There's nothing in the y position or the y velocity, right? And then our z is going to get us 300 cosine 30 t minus 4.9 t squared, and in meters per second, g is going to equal negative 9.8 meters per second squared. So we're going to cover up that real quick, and now we can use this equation to solve for our t. Oh, this should be sine of t, because this actually makes, on our projection right here, this is 30 degrees, and then this is this right here, this distance, let me label that in blue, actually going to be opposite, which is going to be our z, right? So then we can do some quick, not quick, it shouldn't be sine, cosine of 30, it should be cosine of 300, yeah, oof, made some small mistakes on the way. Let me just fix that for you guys. Okay. And now we can say that's going to be 300 cosine of 30, which is going to be 150 t.18 t squared. And then that's going to be, actually no, this is 150 root 3, 150 t minus 4.9 t squared. And now we can solve for our t and the z, because we want to see when t lands, when the projectile is thrown in the air and when it's falling. Because this is the initial direction of the projectile, but then it's eventually going to fall over. So we have t, 150 t, so this equal to 0, t, and then we can say that 4.9 t equals 150 over 4.9, or 30.61 seconds. So now we can solve for where does the projectile land in the x and y direction. So we can just plug that in real quick, and we get 150 root 3 times that for our horizontal, for our x, and our y, we can just use 0.18, and then you can plug this in to your calculators and then just see where it would land respectively. So, and in this case, what I actually got for you guys right here is that's going to be 7,953 meters in the x, and then 168 meters in the y direction. And for part B right here, this is like an extra challenge. This is involving the sum and addition and subtraction of vectors to solve for like the course correction. I'm not going to be going over this in this video, but in the description I will post the solution to this problem, and if you want to, feel free to check your answer for that. And then finally, we have Newton's laws of motion. Again, if you've taken physics, you know that it's just F net equals ma, and your a depends on your direction that you're going in, right? So for example, if we had a problem of if we had like the Atwood problem, right? A classic Atwood problem. You have a block right here, and you have like a massless pulley. A block right here. You have the sum of the blocks in the x and the y direction you have to consider, right? Not just one. And we're considering it to be like static, right? We say that F net and the y equals 0, fx equals 0, right? And you can solve for this, given this, and all of these are just another way of saying a in the x, a in the y, and a in the z. However, that notation gets a little bit more tricky when we are going over partial derivatives, because it's actually another way of writing the notation of it. So it really does depend how you want to write it, right? And this is a vector, also f, because force is also a vector, because if you have a scalar, which is usually mass, times a vector, you're gonna get a vector. It's just like one of the rules that we learned about in the beginning of this channel, in the beginning of this series, right? It's the exact word that we're talking about. And that is pretty much it, covering all of motion in space for section 11.7. Thank you so much for watching. I hope you guys have a fantastic day.